Your seminar is very famous, so it's really an extra honor to be here. So I will tell you all of the definitions of the words on my slide. And in fact, my talk is basically in 3 parts. And in one part, I'll tell you what linear compartment models are. In another part, I'll tell you what identifiability is. I know that many of you do know already. And then at the end, I'll tell you the results on a certain singular locus. Okay, so I like to start my talks with this slide for several reasons. Okay, so the first is to tell you that where I come from. So I'm not a differential algebra. This is sort of my first foray, somewhat touching the area of differential algebra. I'm a math biologist at this point in my life. And so I like to show this slide to remind the audience where we stand, right? So the goal really in math biology is actually to learn something about biology. The goal really is to learn to get some biological insight, okay? And along the way, usually there's a sort of many steps, right? You have some hypothesis, you build a model, and then you might have some experiments that you need to analyze, and then this kind of feedback loop happens around again and again and again. So why I put this slide up today is that I wanted to highlight that one thing, where we stand today is at the model analysis level. We have some model, and we want to know what's going on and what we can know about it in terms of the topic of identifiability. Okay. And another reason I wanted to point this out is that for those of you who are somewhat algebraically inclined, hopefully all of us, there are some very nice algebraic aspects of this whole process: discriminant, matroids, model variety, things like this, right? So if you're interested, I encourage you to take a look at this paper. Okay, so as I said, my talk has 3 parts: linear compartment models I'll introduce first. Second, I will define identifiability, at least how I would like it for this talk. And here is where the differential algebra shows up, okay? And then finally, I'll tell you our new results on a specific singular locus. And this work is joint with Elizabeth Gross and Nicolette Meshcott, who I understand gave a talk here recently. And our paper is on archive, and we're in submission, so we're very interested if you have any comments. Okay, so let's start. Let's start with the biology, and this might even have been a slide that Nikki already showed in the seminar, and possibly in the seminar. But let's start here anyway. So here we're interested in maybe some kind of pharmaceutical application where there's some drug that is given intravenously into the blood, and the goal is to target a specific organ. Okay, and so what somebody in pharmacokinetics might do is to write down all of the possible places the drug could go, right? So the drug is put into the bloodstream. It could get lost or degraded in the blood. There's some exchange into the organ that you're targeting, and then of course there could be some loss as well. So here's the basic picture, and the other thing here is that what can be done is measure the drug in the blood. Okay, so you can't actually measure how much drug there is in the heart, right? Even though, of course, that's what you actually want to know. You want to know how much. Well, one of the many things you would like to know is how much blood how much of the drug at any time is in the heart, for example. Okay. So this is a very common application, and all drug companies use these types of models, as we'll see, and they're very, very much interested in this question of identifying the parameters, knowing how quickly the drug goes from the blood into the heart, and vice versa. All of these parameters they very, very much like to know, and very much use this type of analyses. Okay, so any questions about the application?
So they could measure it in the heart, but they just don't want to.
Okay, yeah, that's true. That's true. It would be very, either dangerous or whatever. Yeah, exactly. So you're right. Sometimes you could, but maybe it's either costly or intractable or okay, good. Or we want to make many measurements, right? That would be very difficult. Yeah. Okay, so let's turn the model into the sort of biology picture into sort of more mathematical picture. So it's redrawn here. We have 2 what are called compartments. So X1 and X2. Okay, those are the 2 places the drug could be. So we call it a compartment model or compartmental model, right? And we can write down the corresponding differential equations. They're, in this case, and for the entire talk, linear differential equations, okay? But of course, one goal going forward is to do many more non-linear models, right? But for today, we're just focusing on linear models. So the edges the arrows tell you where these corresponding terms of the differential equations are. I have two differential equations, one for x1 and one for x2, okay? And then the extra interesting thing beyond what we teach maybe our students in linear algebra and differential equations is that we have an input term. This is the drug coming in, that's a u right here, okay? And inputs are always called u in this area. And then the output is y, and again, y is always what the output here, so y means it's the measurement, okay? So what I can measure is the amount of drug in x1. So the question we're interested in today is whether we can recover all of these parameters kij given these data u1 and y1. So if we had perfect input-output data, so we know exactly what the values of these u's are at many time points and the corresponding values of the y's at many time points, can I then recover all of these kijs?
Are the variables k something, are they constant or are they vary with time?
Here we're assuming that they're constant. Yeah, here they're constant. But the u varies in time. That is supposed to be controlled. The drug input is supposed to be controlled, so that's a function of time. But the k's are constant. Okay, and so this, and to clarify, right, here I'm interested in what's called structural identifiability, which means assuming that I have perfect measurements of data, right? Can I do this? And then of course the question in real applications is practical identifiability, which means when I have real noise, real data with noise. Okay, but of course if you aren't even structurally identifiable, you aren't going to be even practically identifiable. Okay, and one of the discussions we already had this afternoon is that this is not exactly a definition, right? This is a good intuition, right? But one thing we need to do is to really nail down what this definition of identifiability should be. That will be in a few slides, and then we'll go from there.
Are you absolutely sure that structural identifiability, without that, you don't have practical?
I'm not 100% sure. No, you're right. I'm not 100% sure, but at least that's the guiding intuition. Let's say that.
Okay.
Yeah. Okay. I don't have any theorem. No. Yeah. Because partly it's because I don't do practical identifiability at this point in my life. But certainly there would have to be some hypotheses on what kind of noise and so on in order to write down such a theorem.
Noise can be used.
Yeah, absolutely. You're right. There are theorems in that direction. So, maybe I was overstating myself. Yeah, that's a good point. Okay. Okay. Good. So then, this one. So there are many different approaches to identifiability. The approach that I'll take for this seminar is for the differential algebra approach. One thing I wanted to highlight is that there's no complete classification, even of linear models, of which ones are identifiable, right? This is surprising, right? I'm just writing down some very simple linear ODEs, and if I just wrote down one of these graphs with maybe like 4 compartments, and I put in a few inputs and outputs, without doing the differential algebra, I wouldn't know immediately which one, whether it was identifiable or not. Surprisingly, there's no theorem like this. And on the other hand, I don't expect a theorem that says they look exactly like this and not like this. There's not going to be some easy
So the open question is for linear models too?
Yes, right. I mean, so if you gave me one with 6 things, I would plug it in and get the answer, right? But I would like a theorem that would more completely classify it, so I wouldn't have to do this every time.
One can do it with software, but you have to wait until the software finishes.
Okay.
So it's not that it's impossible. There are algorithms to answer this question.
Right.
I think what she means by classification is instantaneous answer,
I understand.
rather than answer you check on each.
Yeah, look at
I completely got
and
exactly.
know.
Yeah.
Yes.
Exactly. And so we'll have some theorems in this direction now, right? I know the answer to this question, right? But we would like to know in advance. Yeah. Okay. So of course I think this is in some sense some kind of holy grail. Like maybe if there was a nice classification up until n equals 6, right? Something 6 compartments. Even that is very useful because those are maybe the most common ones, right? There are some in the literature with like 18 compartments, but those are much more rare.
So you limit by the number of compartments rather than by the number of parameters?
That would be my intuition based on the examples coming from biology, but that's not necessarily the right. Maybe somebody else would think of a different way. Yeah, this is just my own. That's where I would start. Yeah. Mm-hmm. But you're right. That's in some sense the question, right? The more parameters, the harder it will be. Yeah. Okay, so let me tell you the way we're going, okay? So we're going to start with a linear compartment model, right? So we have some number of compartments and they're connected in some ways. We write down the linear ODEs. For this slide, we know we'll let M be the number of compartments. Okay, so we had M equals 2 so far. So an input-output equation is an equation that holds along any solution of the ODEs, okay, comma, that only involves the variables that you can measure, okay? So the input variables, right, the drug input, the output variables, whatever you can measure, okay? And of course the parameters will be inside because everything depends on the parameters. And also I'm allowed to have these variables and their derivatives, okay? Okay, so just as an example of what these input-output equations could look like, in this case, for this case of 2 compartments, so this is the model we had before. The input is the drug here, here's the output measurement, and then here are these degradation terms. We call them leaks in this area. This is an example of an input-output equation. So I tried to, the colors, I tried to be suggestive. Output is always purple. So on the left-hand side, I have these purple variables, y1, the derivative of y1, and then the second derivative of y1. On the right-hand side, in blue, I have the input variable u1. So this says that along any solution of the ODEs coming from the system, it's always the case that that y1 and its derivatives satisfy this equation with respect to the equation the solution u1. Okay. So one of our goals in this talk is to explain this possibly mysterious input-output equation, okay, and then use it to get some of our newer results. And then one quick comment that I was just discussing earlier this afternoon is that these input-output equations, there can be some interesting pathological examples where you cannot get an input-output equation. Okay? And then, however, for these linear models that we're talking about today, we will always have these, so we'll be safe. Okay. Okay, so where do they come from? So either it's clear to you where they come from because you come from differential algebra, or let me try to explain. So what am I trying to do, right? I'm trying to eliminate the variables that I can't measure, right? So I can't measure x2, so I want to eliminate it from any of the ODEs, okay? So that's exactly what I want to do. So I would put the differential equations into some differential ideal, right? And then do the elimination to get rid of the xi's, okay? Or one thing we could do is we could take the differential equations and then we would take enough derivatives as there are a number of compartments. Okay. So in the case of these linear models, we know that that's enough, so the stopping criterion is already there, right? We know that's enough derivatives to take, and then this is just a regular elimination problem. Okay, and so I was trying to indicate that here. Okay.
So when you write polynomials, you polynomials in derivatives also. When you intersect with polynomials in u and y.
Yeah, so these are polynomials and the u's and the y's, exactly.
And the derivatives.
Oh, yeah, that's missing. Absolutely, yep. Yeah. That was wrong, yep. And their derivatives, yeah.
What are the ranges of I and J here?
I and J. For the output equations. Okay, so in advance, it's you specify which are output variables, okay? And you just write down those equations. So in this case, you would write y1 is equal to u, or u1 is equal to y1, yeah. So there's some specified ones, okay, yeah. That's part of the setup which is hidden in this model.
So what is meant by their M derivatives? First order? You mean first order?
You can, right, so you take m up to the derivative, up to m derivatives of this.
But m is used already.
That's the same m. So it's a result. This is hidden here. It's a theorem that you only need to go this far for linear equations. Yes, exactly. Not my theorem. Yep. Other questions? This is great. Okay, good. So where do these input-output equations come from? Okay, so you know now, but now we want a formula for them, and that was what was given by Meshkat, Seth Sullivan, and Marissa Eisenberg in 2015. So they have a nice formula that looks like this, okay? And so let me tell you where it comes from. So you start with your model.
Can I ask a question?
Yeah.
It's sort of sounds like a grammar question.
Yes.
So before you said an input possible,
yeah.
you say the input.
Yeah. Okay, good. This is important. So of course, input-output equations can be any polynomial in this ideal, right? Okay. In all of the models we'll be looking at today, I only have one output, and one input in the same compartment. And in this case, it's a principal ideal. So when I say the input-output equation, I mean the generator up to sign, of course, or whatever, up to units. Okay. So today there will only be one input-output equation. Yeah. This proposition is actually quite much more general. And then they would list a one input-output equation for each of the output variables. And then their theorem is that those are algebraically independent and they generate the let's say ideal or differential ideal. Yeah. Mm-hmm. Yeah. So in I want to say some algebraically independent generating set, let's say. Okay, good. So here's the recipe. I write the differential equations. I write them as regular linear ODEs. So I have some matrix A. Okay. And this matrix is basically the if you know what the Laplacian matrix is. So on the off diagonal, I would have K1, 2 because I have this edge from 2 to 1, right? And on the diagonal, I would have, if I had K21 here, I have a minus K21 here, okay? But then since there are these leak terms, these degradation terms, I have to also add a minus K01 and minus K02 here. Okay, so it's not quite what we would call the graph Laplacian because I also have these degradation terms. But in any case, it's exactly the matrix that gives you the linear ODEs, and then but we're also, right, adding in this input equation, okay? So I have this input term here as well into the ODEs. So then this matrix A, okay, is the sort of key component that goes into the, in this case, the input-output equation. So the hypotheses are, at least in this very special case that I stated, when you have a model that's strongly connected, so here we have edges between 1 and 2, so you're strongly connected. In this case, I just assume we have input-output only in compartment 1 for simplicity. But the proposition is much more general. And you have at least one of these leak terms, one of these degradation terms. Okay? And that's just to make sure that this matrix is full rank. And then in that case, the input-output equation has this form, which I will show an example of on the next slide.
Question?
Yes.
So does strongly connected mean that each compartment is connected to each other compartment
Yes.
directly?
Not directly, but could be
But
through
by a chain.
By a
Okay.
chain, precisely. Yep, exactly. And in both directions. That's exactly right. I believe that they have some under some. I think they can weaken it a little bit, but I can't. But I would have to dig back in their paper.
Okay.
Yeah. But for today, let's just focus on these.
What's the boundary of I or what?
The boundary of let me show you in this picture. The boundary is the formal derivative operator. Okay. So so an example of this equation is for this network. So this boundary condition is really this derivative. Okay. So when I have ddt to the third, right, I just mean I'm taking the third derivative of y1. It's sort of a convenient notation that we'll use to get to the input-output equation. Okay. Okay. Good. So and then the only other piece I think I didn't quite define is this sub 1, 1. What this means is that I take the original matrix, so here's this matrix here, and then I remove the first row and I remove the first column, and then whatever's that sub matrix left is what I have here. Okay. Okay, and then you multiply by y1 or you multiply by u1 on the left or the right hand side, and then you end up with this input-output equation. Okay, so these terms are basically terms coming out of this determinantal expansion. Any questions? Okay, so
The size of the matrix is what? M by M or?
is yes, m by m, where m is the number of compartments, exactly. And then the next one will be m minus 1 by m minus 1. Yeah, exactly. Okay, and that sort of hints, right, that that's why you need that many derivatives. Yeah, I mean that's part of the theorem in some sense, right? Yeah. Okay, good. Okay, so proof. So again, this is not my proof, this is the Meshkat-Sullivan-Eisenberg result, but I think it's a little bit nice to see, okay? So I'm trying to prove this result, right? So I write down the differential equations as I did before, okay? I can move the a to the other side and rewrite it like this, okay? And again, this is the sort of formal derivative operator. And then, right, so now I have basically a matrix times x equals u, and so you can just use Cramer's rule, right? So I can solve for x in this way. I can take the matrix where I replace column 1 by u, okay? Take its determinant, and then divide by the determinant of the original matrix. And Cramer's rule tells you, right, you have your variable x1. So then the only thing left to get back to the actual result, right, is that I just need to compute the derivative of the top, right? And then in this case, I only, so what is u? U is the input variable, right? I only have one input variable, right? So my vector u is u1 and then 0, 0, 0, 0, 0, 0, 0, right? So if I do Laplace expansion for to compute this determinant along that column, it's very easy, right? And then you get back basically this determinant here, move this to the other side, and then we get this equation here. Okay. So the message here is that for linear ODEs, right, computing the input-output equation is just linear algebra, right? It's just Cramer's rule, and so we can get it without having to plug it into DAISY or any of these other differential algebra softwares. Okay. But as I said before, one of the goals, right, is for me anyways, to go and to do more nonlinear models where we don't use Cramer's rule, okay? Or cannot, right? Okay. Okay, so last thing before we move on, let's look again at these coefficients of the input-output equations. Okay, so let me see. Okay, yeah, so I guess I'm jumping a little bit ahead. So they come from the expansions of these determinants. Okay, so I want to ask the question, we want to be able to understand these coefficients that will help us get towards identifiability. So when you look at these coefficients, what patterns do you see? In other words, can you state what the theorem is supposed to be for what each coefficient should be? So like, what is the coefficient of the first derivative of y supposed to be in terms of this graph? What patterns do you see or what ideas?
You'll just show the answer.
I already showed the answer. Oh, okay, so everybody doesn't want to say anything because they saw the answer and they're embarrassed to say the answer. Okay, good. Okay, so right, so the degrees are sort of clear, right? If it's a second derivative, I have a linear coefficient, right? If it's a first derivative, I have a degree 2 coefficient, right? So if I look at these sort of, for example, k1, 2, k2, 3, right? That's k1, 2, k2, 3 here, right? So one thing you can see, right, is when you do determinant expansions, you're picking one thing from each row and column, right? So I can't have an edge coming out of 2 and then another edge coming out of 2. So I can't have k1, 2, k3, 2, okay, for example. So these all correspond to sets of edges that don't make cycles and don't have 2 edges coming out, okay? So a graph theorist would say, well, these are built from what are called trees, right? These directed trees, or in other words, forests. Okay, and then the number of edges plus maybe plus which derivative is should equal 3 in this specific case. Okay, so and then similarly for the one on the other side, right, we removed row 1 and column 1, so that's like removing 1 from this model into this model, right? And this k1, 2 all of a sudden turns into a leak, basically. Okay, so again on the u side too, we also are basically taking sums. Each of the coefficients corresponds to some forests in this model. So that's our first theorem, that each of these coefficients corresponds to forests exactly in the manner that I described. Okay. So why do we care about the coefficients? The reason is because these coefficients are how, at least for this talk and for our work, we're going to define identifiability. Okay? So what we say is the idea is that this is an equation that holds along any solution of the ODEs. Okay, so if I have many instances of time where I can measure these things, my data are so perfect that I can compute third and second and first derivatives. Okay, then if I have many values of this, let's say in this case I only have 5 coefficients, so I just need to take maybe 5 samples, then I can write down a corresponding linear system and solve for these coefficients. So I have a linear system, I solve for the coefficients, and I get all of these coefficients. Okay, so my data are perfect, I get coefficients. So then the question is, okay, so now I know the values of these coefficients, can I then recover the parameters? That's the question I'm asking, okay? So our definition is, for identifiability, is given these actual values of the coefficients, right, these sums, can you then recover the KIJs?
Did you say again how you find the coefficients?
So the idea is that we have such perfect data that for many time instances, I can evaluate u1, the first derivative, and the second derivative of u1. And I also have the same for y1. Okay, so at some time point I write down these numbers, and then I do it again for another time point, another time point, another time point, another time point, and then I'm just basically solving a linear system for these coefficients.
Why is it linear?
It's linear in y1, so if I have numbers for these.
Yeah, but it's not linear in the case.
No. So, but I want the actual value of the coefficient. So this complete. All I can recover is right at the moment is the stuff inside of the parentheses, not the, yeah. Exactly. So I can recover the stuff inside of one of these parentheses blocks, and then the question I'm interested in is if I just have this sum and this sum and this sum and this sum. Let's say if I wrote it down, right? Okay, I have all of these sums. Now can I go back and recover the case?
Right.
Yeah. Okay. Do you see my question yet?
Yes.
So could you give a simple example on the board maybe?
Yes. Okay. So.
Maybe on this one.
Sure. Okay. So let's say that your equation is extremely simple, like y1 is plus. So I have some coefficient plus y1 plus y1 is equal to some other coefficient. Okay, and then maybe for simplicity, it just is equal to this times x1 or u1. Okay, so each of these are coefficients. Okay, so if I know some values for these at some time points, I plug them in. I know some other values, and let's plug them in. So if I have 3 of them, okay. So then you can write this as a matrix. Maybe this is like it would be something like A, some matrix. Maybe I say B. Okay. Times something equals my data point, those sort of data points. Okay. So I basically just have a linear system. I have numbers that I'm plugging in for these several times, and then I can recover the 3 coefficients.
So are you sure that the data that you got are linearly independent of?
No, exactly. So that's completely on the practical side, but you're right. You would have to make sure for some way, right, that you have enough data and that they're independent enough to recover that. Yes. Okay. Exactly. So that's sort of hidden inside of this definition. I completely agree. Yeah. Okay, good. So now we assume we can get the coefficients, right? One of them looks like this, for example. Now we want to go to the next question is then can I go back and recover the original parameters, which is what I actually want. Okay, so let me clarify a couple of things. Here I mean generic, so off of a set of measure 0, I want to be able to make sure that this map is actually injective. And I also mean locally, so if there are finitely many parameter vectors that map to the same one, that's okay for me as well, for today's talk.
Why do you say R? Is it indeed R what you're checking or not?
In this case, for the linear things, it will not matter. Which, yeah, because really, in practice, these will be R plus and R plus, right? Because they're only positive, or let's say non-negative parameters. So that's actually the question I'm actually interested in would be from non-negative numbers to non-negative real numbers, for example.
So I mean, it's not complex. It's not algebraically closed field. You're actually doing R.
The results won't matter because they will be easy to. Can you wait me a couple minutes? It won't matter because the measure 0 set will be clear either way, wherever you work. Yeah. Because everything is very linear in this setting, so it's not going to be an issue.
I believe the question could,
No? Okay, sorry.
be.
Yeah.
The question could
Yeah.
In practice, of course, these cases are real.
Yeah.
But once you have an algebraic system, when you are able to solve for the case,
Yeah.
it could turn out to be complex.
Yes.
Or you, yeah, right?
Yes. So.
What do you do? Is it valid or?
In this case, it's so let's say it's never come up with in any of the models that we'll be looking at today, and I don't expect it to. But you're right. I don't see why I don't see an obstruction to having some issue be like that. Yeah. Because for example, because sometimes that happens, right? Is that you'll have a unique positive solution, but then you have a bunch of complex ones to which you disregard. In this case, I would be okay because I only care locally, and as long as it's finitely many, I'm safe.
What do you mean by locally?
Locally, I mean that I want this map to be finite to 1, at least generically. Yeah, finite to 1 generically.
Could you define generically?
Generically means the set on which you don't have finite to 1 is a measure 0 set.
Which means?
Measure 0 set?
Yes.
In this case, okay, so.
That's plenty.
in this case, for this talk, all of them will be actual hypersurfaces, so we will be safe. I won't have to define it any more strongly than that. Yeah, good question. Other questions? Okay, so if you had something like this, you might try first to solve it by hand, okay? Or you could just say, well, if I want to be locally identifiable, this is the same thing as making sure that the corresponding Jacobian matrix, at least generically, has full rank equal to the number of parameters. So in this case, it should be rank 5. Okay.
So the implicit function theorem, yes.
Precisely, exactly. That's exactly what we're appealing to here. Okay, good. Other questions? Oh yes, generically. Yes. So in fact, that's what the focus of the last part of the talk now is on this generically, because most people in applications, once you know you're generically identifiable, generically locally identifiable, you feel safe. You feel like, okay, now I'm set. Now I can collect my data and so on. Today for the talk, I want to know where it is that you have the bad locus. Okay, because even if you're close, things can go badly wrong, and I want to know where this is. Okay, so that's the rest of the talk, is this what we call the singular locus, and we want to know where does identifiability go wrong, and then knowing that information, does that affect applications or not? Okay, so the singular locus is where you cannot identify the parameters because there are infinitely many that map to the same data vectors. So in other words, it's when the corresponding Jacobian matrix is rank deficient. So here's an example that we're still using, right? If you take, so there was this coefficient map, right? This map, you could relatively easily write down the Jacobian matrix, take its determinant, right? I mean, of course, we use a computer to do that, and we get this nice equation for the equation of the singular locus. Okay, so this tells me that if k12, if any of these kind of green colored parameters are 0, then we have a problem, and we can no longer identify the parameters. And in some sense, this is a good thing from the biological point of view, because this, if you know you have a system where the bloodstream is going into this other organ and going to this, none of these are turning off, right? And then you feel safe. Okay, so for sure I can do my identifiability problem. Okay, so here's the first example. Okay, so the first result in this direction is that at least one of the reasons we were first interested in the singular locus is maybe this tells me information about submodels, right? Maybe this tells me about whether or not I can set this or I can remove this edge.
Okay. By the way, so this says that at least some of the parameters are not identifiable, right? It doesn't say that all.
Yes. Right. I completely agree.
And
we don't distinguish that.
It doesn't.
Right, but we didn't even look at the problem, so I don't know the answer.
Why?
Yeah.
Are you saying the K12 here are not identifiable?
I'm saying that if K12 is 0, then the corresponding vector, I cannot recover the entire. If I have data, I cannot recover the original. Because there's an entire.
So you already know K12 is 0, and you already know.
No, we don't know. We're assuming we don't know, and we're just collecting data, right? And if it happened that data came from here, then there would.
But you can get the identity that the determinant, let's say, is. Okay, sorry.
Yeah, but this would be like the analysis you would do before you start the experiment.
The Jacobian is a function, and you don't know it's 0.
Right, exactly. Yeah. Exactly. Yeah. Okay, good. Okay, so one of our goals is to say, okay, maybe this tells us about which edges I can shut off and keep identifiability or not keep identifiability. And that's our first result. So so here's the setup. Let's say you have a model M and you already know it's identifiable. Okay? And now I remove some more edges from this model and I have a new model M tilde. Okay. So now I want to use the original singular locus equation, F. Okay? And I want to ask the following question. So I want to plug in, I want to know when I plug in the corresponding k's equal to 0, right? So I deleted some edges. If I plug in those k's and set them equal to 0, do I get the 0 polynomial or do I not get the 0 polynomial? That's my question. As long as I don't get the 0 polynomial, then the new model, the smaller I model I have, is still identifiable.
Could you explain this motivation maybe a little more about drug targets?
Yeah, okay. So what is this? Maybe the picture will help. So imagine that this is my model, okay? And here is my equation for the singular locus, okay? Here is a red edge, which is not in the monomial part, okay? So when I plug k23 equal to 0, I don't get 0 for my singular locus. So what this theorem tells me is that I'm allowed to remove this edge, and I still keep my identifiable model. So from the biological point of view, this says, well, maybe for some reason this edge can be targeted by a drug, and this edge can get turned off. So the drug can no longer go from this organ to this organ. Okay, but you would want to know is in the resulting model, is it still identifiable, right? Can I still identify parameters so that I can understand how my drug works?
I don't understand the biological part of it.
Because I'm interested in shutting this. So the question is setting this equal to 0, right?
How can you shut it off? How can you make drug not to go somewhere?
There can be depending on the situation, right? There could be some physical barrier, or there could be some way that organ, like sometimes there are some receptors or some parts of the drug that allow the drug to come in, and maybe those get shut off in some way.
Yeah, that's true.
I mean, it's at this point, I don't have a very
Many reasons.
many reasons, right?
Your kidneys.
Yeah, exactly. And it's also the other way around. It's a theoretical question too, because you could say, I would like to target this, and then on the experimental side, they can try to investigate whether that's possible and how it's possible, right? So, yeah, both points of view.
I mean, using just one rate from one organ to the other, independent of all the biology and chemistry there, it's very simplified.
Sure, yeah.
So what the definition of singular locus is just the hypersurface where Jacobian vanishes.
Yes.
Or it's the set of points where primes are not identifiable. It's the same.
In the models that I was showing today, it's the same.
According to the definition, it's the same.
No, it's a union of Zariski open sets.
Exactly. In general, it might be, but we've never found an example yet. But I'm sure I could find.
No, I have a paper on it.
Okay, good. So now I'm happy to be here. Yes, good. I would love to see this.
I have just a paper.
Okay, perfect. Thank you. Yes. So there.
I think she defined identifiability by the Jacobian.
Yeah, right.
Okay, but then the point is that this Jacobian might not be square. Okay, so right, this I made some beautiful example where they're square matrices. What if they're long rectangles?
Yeah.
And then the problem you're describing can show up. We had never found one, but now I will find. Now I have one. You will tell me. Perfect. Yeah.
So just what's the title? Parametric linear equation.
Okay.
Linear equation.
Okay, great.
Which
Exactly.
is exactly what this is.
Yeah. Perfect. Good. Exactly. So we had never found an example, but now we were looking for one. Yeah. Good.
I mean, there is an algorithm to actually find out all the cases.
Okay. Yeah. Okay. Very nice. Okay, good. So, okay, but then I also want to mention that the converse is false. So, for example, if K12 and K23, imagine I wanted to turn both of them off. Okay. So I might imagine here K12, if I set K12 equals 0, this is all of a sudden vanishing, right? But the whole parameter space has kind of shrunk by 2, right? So I can't use the converse of this theorem because it's false. And in fact, deleting 2 of them actually keeps it identifiable, which is a bit of a mystery. And if you look, since that'll come in the next slide, if you delete K12 and K23, then what's left is basically this cycle in one direction. And then that's our next result. So some common models include the cycle model, and then also this mammillary star
That's
model.
why I asked earlier whether your K's are constant.
Oh, okay.
Because, if you have cycles or something like that, then the concentration in the compartment could decrease with time, and therefore the rates would change.
So, but the rate, but in the derivative, it's the rate times the amount in that compartment, right?
Right. Yeah.
So, but the rate itself, I would argue, is fixed.
I see.
Yeah. Right. So it's like K12 times X1, right? And then X1 will decrease, but K12 will be constant. That's the thinking I have. But okay, you're right. I mean,
yeah. It's all right. It's a good assumption.
Okay, good. So, okay, so then what we did is we computed the singular locus equations for any n, right? And then, we computed for several and then proved the result for general n. And you're not supposed to look at these equations except for, to note that the monomial part seems to always be these edges that are getting towards 1, going towards the first component, right? So kind of seeing here, they're kind of all going towards the component 1. Okay, so we tried this also for so I think I've been showing you these first and second. I've been showing these networks for a few slides, and then what I'm showing in this picture are the exponents of that monomial part. Okay, so the exponent is sort of 1, 1, 2, 1, 2, 3, right? And so the pattern is sort of clear, right? And there's sort of an obvious proof by induction, but we cannot do the inductive step. So we have just a conjecture that this pattern of exponents continues.
Can you explain what catenary models are?
Oh, catenary. So they're they're called catenary. In the literature, they're these path models, right? Where the directed graph is just a bidirected path all the way. Yeah. Mm-hmm. I only use this because in the identifiability literature, these compartment model literature, they call them catenary models. Yeah.
So even if some of the weights are 0.
Some of the weights are 0. No. That's exactly the point, right? Is that so in the equation for the singular locus, this rate appears to the power of 1. This rate appears to the power of 2. Yeah, exactly. So that's exactly what tells you they cannot be 0, right? Yeah, exactly. But it's interesting because some of them have rate 0, right? Exponent 0, which means that they are allowed to be 0, for example. Yeah.
Why would you be interested in exponents greater than 1? Like,
yeah.
Why do you care about it?
So you're right. I'm not actually interested in the exponents as long as they're greater than 1. But I don't know how to prove this result except saying the determinant of the Jacobian equals blah blah blah. So
okay.
You're right. I mean, I don't know any other way because I want the radical, right, of this idea,
Right.
let's say. But I don't know how to get it any other way.
Okay.
Yeah. So we can prove a little bit. We can prove that maybe most of these terms do divide the equation of the singular locus, but that's kind of where we are at the moment. Yeah. Okay, other questions? Okay, so now let's look at these kind of patterns 1, 2, 3, 0, 1, 2. So 1, 2, 3, 0, 1, 2. You can, in this bigger tree network, right? This model, again, you see this kind of 1, 2, 0, 1, 1, 0 patterns kind of getting as you go from the sort of leaves of the model all the way back in. And then the only interesting thing is that this node 2, there's sort of an interesting way that you add the incoming exponents in to get the new exponents. Okay, it's, in my opinion, a complete mystery. And this pattern was discovered by 3 of my REU students last summer, and they have this nice conjecture, which they checked up until maybe 6 compartments or something like this, that says as long as you have a tree, okay, maybe bidirected tree, okay, these exponents generalize kind of this pattern that I'm trying to hint at with these students.
Could you explain what the addition of the exponents mean?
So what does it mean? Okay, so where does it come from? Okay, yeah. So here it is so here you would come in 1, 2, and then you expect this to be 3. Here you would have 1, and this would expect to be 2. Okay, so right, because here it would be 1, 2, and then you would expect this one to be 3. Here it's 1, you would expect to be 2. Yeah, so here the pattern is you take the 2, you take the 1, and then you add a 1, and you get 4. Okay. But then when you're coming out, you have 0, 1, then you expect 2. You have 0, and then you expect 1, and then you just add them. I mean, right, my students did many examples, and this is what they found as their pattern. We don't understand it. But again, we're not, like you said, we're not actually interested in the exponents except that they're greater than 1, greater than 0, really, I guess. But on the other hand, we don't know how to prove any kind of result without actually getting the actual equation. Yeah. Other questions?
But like maybe you can just like remove this edge and show that the model is not identifiable, like finding a symmetry or whatever, or it's not.
So that would be one direction, right? That you would say that that would prove that the corresponding monomial divides the singular locus equation.
Yes.
But then the other direction, we don't know how to do, right? Unless you actually get all the way to the determinant of the Jacobian, and then in which case the 2 degrees would match up, and then this is the degree of this polynomial because the degree of this polynomial, and then you know it's equal on the nose. That's the only way we know how to do it.
Okay.
Yeah. Other questions? Okay, so then the last result, I just have one slide, is about the identifiability degree. So one thing we've been kind of a little bit hiding under the rug is that we're interested in these finite to one maps, right? So you have some input-output, you have some nice input-output data, and then maybe 6 different parameter vectors matched to the same thing, and you're okay with this. Okay. What we wanted to do is to get our hands on a bit more carefully what this number is. This number 6 or whatever it is. So we call the identifiability degree the number of parameter vectors that match generic input-output data. So what was already known is for the path
always
model.
finite?
Assuming you're right, assuming it's locally identifiable, then I believe that it should just be a one number. That generically they should all be the same number. But I have not even.
Okay.
Yeah.
You assume it is finite to one.
Yes. Assuming it is.
Mhm.
Yeah. So hidden, like in our paper, we would say assume it is generically identifiable. Then here's the definition. Yeah. So for the path and the star models, the catenary and mammillary models, the identifiability degrees were already known. Okay, and the star one is something that's not too hard to understand because, right, there's such symmetry amongst these n-1 components, right? There's for sure you can permute any of this. If you're only measuring from compartment 1, how can you distinguish compartments 2 through n anyway? So n-1 factorial is completely unsurprising there. Okay, and then what we did is I think the cycle one. Okay, which again is n-1 factorial, which sort of captures the fact that the cycle has a symmetry, but in some sense the symmetry is broken when you pick compartment 1. So it was a little bit mysterious. I mean, we had to prove it, right, to get to this degree here.
But like, do you know what is the transformation of one set of parameters to another, which are indistinguishable?
Yes. I don't remember off the top of my head, but it is. I mean, when
So
we
it's
proved
not,
it, we
it's
figured
not
it out.
like permutation. It's something more.
Yeah, I want to say something like you only recover maybe like the elementary symmetric functions on those variables or something, and so those can still be permuted. I can't remember. I have to think. Yeah.
So does this degree come from the dimension of some space, or does it come from combinatorics?
I think it's more on the combinatorics. I mean, like we said, we only proved one result in this direction, but so I can't see it as being the dimension of something off the top of my head, but it could be. We just don't. I mean, yeah, I don't have any theory yet for this. Yeah. Okay, and then let me just end by saying that, of course, my goal, right, is to get into the nonlinear models that I usually study off in my sort of usual setting as a math biologist. But our first foray was really into this linear setting with the goal of going towards these nonlinear models as well. Okay, so in summary, I hope to have convinced you that the singular locus is an interesting object, and it hopefully will help us answer one of the big questions of which linear compartment models are identifiable and which ones are not. Okay, thank you.
So no result on nonlinear compartment models?
None, but only because of neglect, not because, yeah, I mean, right? Yeah. Right, none. None yet, yeah.
Not even simple cases like the toilet tank?
So there are, so let me just say that actually there are many, all I mean is that in our paper, in our work, we don't have any on this, on nonlinear models, but there's a whole literature already, and so I'm sure that they're,
Okay.
yeah. Yeah. Linear compartment models are extremely well studied.
So in your examples, singular locus is always divisible either by one variable or by difference. Is it correct?
No, I think
Or you
they
have
got
some
much more
other-
I think they get much more
Or
complicated.
maybe I just missed. So
there's
differences.
here, for example, it's a little bit more
so it
confusing.
can. Okay, I see.
Yeah.
And you don't know what does that mean?
No.
Okay.
Basically, it's just a factorization of Jacobian, right?
Yeah, but it
Sure,
could, it,
yeah.
it, it,
In some
could,
sense
it could
that's
have
what
some
it-
material sense.
I mean, for a particular
It's-
rec, for a particular...
Sure, of course.
Some matrix.
Yeah.
Okay.
More questions?
So do you know when there is a monomial factor?
No. I would expect always, but this is again based on very, very limited examples. So I don't know. I would assume always, but I don't know why. Yeah. Yeah. That's a good question. Yeah.
Other questions? Phyllis, your question?
What
Just
are,
thinking about Jacobian, but
what other
Yeah,
questions
yeah.
besides
Computer
identifiability would be of interest to biologists, like invertibility and
is in
things like
there.
that?
Oh, no, constant.
It's a Jacobian polynomial map.
Yeah. The other, yeah,
The
right.
other thing, you're thinking
The K's, KIJs are constants, they're not
Yeah,
functions, which would make a difference. Okay, thank you.
They're indeterminate, actually,
Yeah,
but they're
probably.
constant.
Sure. Right. Exact constant information. Yeah. So I would love to have theorems. So let's maybe draw a picture like this.
It's D times K, it's D of K.
So if you look, for example, at
Right
this,
or
so
what?
the models I look at a lot in biology have a lot of modular structure. So this network here, and then this network here, and then this network here are basically the same model attached to each other. Okay. So so Nikki Meshkat and I have done some examples where we looked at some of these small ones and seen which ones are identifiable. But if I were to when we try to put all of this into DAISY, it just tells us it just cannot handle something of this size,
Into
right? Into DAISY, a software package for checking identifiability for nonlinear models.
Okay.
But what we would love are theorems that say, and we've started to get some, right, that say, okay, so if this one's identifiable, and it's only connected in this specific way, then the whole thing is identifiable. Things like this.
What are the black dots and the white?
Okay, so this
Input
is,
and output?
no. This is saying that there are several ways of this mechanism. So you can see that the goal is for this enzyme to put these black dots basically onto the substrate, onto this S, okay? And there's several mechanisms. One of them is this sort of gray shaded one, and one is this more complicated one here. And these are sort of two extremes of this type of mechanism, right? And so there are many interesting models in between as well, right? And there's the dynamics are very interesting, and we have some conjectures on the identifiability and so on, but just as a start. Yeah.
Why is the mammillary model called a mammillary model?
So I think it's okay. So so it's a star graph, right? So there's something in the middle, and then you have all these things coming out. So sort of like a mammallogram with something in the middle, and these kind of outputs coming in.
Okay.
Yeah. But again, it was invented before us.
Of the drugs for breast cancer, it's not a model.
It's not specific to, no, it's prior to that, but it is a case where you normally have the blood in the
Right,
center, and then it's
right.
diffusing to all possible
Right.
organs, right?
Right.
Yeah.
Yeah.
More questions?
Fascinating.
Okay, thank you.
Thank you.